Kinetics, lesson number 7, kinetic energy distributions. Let's first start by drawing a kinetic energy distribution using the axes where the y-axis is representative of the number of molecules and the x-axis is kinetic energy. A kinetic energy distribution will start at the origin and look something like this. The area underneath the curve represents the number of reactant molecules that we have available. So I'm going to go in and starting from the left-hand side, I'm going to draw in reactant molecules. If you would like, you can draw reactant molecules underneath the entire curve. I am not going to do that. I'm just going to draw reactant molecules on the left-hand side and also on the right-hand side. But again, you can go ahead and draw reactant molecules underneath the entire curve for yourself. Okay, so the molecules on the left-hand side of the distribution are moving with a low kinetic energy, and since they have a very low kinetic energy, they would be moving very slowly. The molecules to the right side of the distribution would be moving with a high kinetic energy, and therefore would be moving fast. All chemical reactions have an energy barrier. And this energy barrier relates to the formation of products and collision theory back in lesson 5. The molecules to the right of the energy barrier, these molecules here, have sufficient kinetic energy to form products. When they collide, they have enough kinetic energy to break bonds, rearrange, and form products. The molecules to the left of the energy barrier do not have sufficient kinetic energy, so when they collide, their collision results in the reactant molecules just bouncing apart without forming products, as there's not enough energy to form bonds. Let's look at what happens to the kinetic energy distribution when we increase the temperature. When the temperature is increased, the average kinetic energy is increased. There are fewer slow molecules and more fast-moving molecules. So let's look at how this distribution changes at a low temperature and at a high temperature. Same axes as we started with, number of molecules on the y-axis, kinetic energy on the x-axis. At a low temperature, my kinetic energy distribution may look like so. And we'll say that the temperature that I'm going to choose is 25 degrees Celsius. We would also have the energy barrier here. And it is the molecules to the right of the energy barrier that are able to form products with sufficient kinetic energy. If we increase the temperature, one of the things that we have to note is that we do not change the number of molecules by increasing the temperature. We have exactly the same number of molecules. So the area underneath the curve must remain the same. But the curve changes because at a higher temperature, we're going to have more faster moving molecules. So at a higher temperature, the curve would look something like this. And let's say that this is representative of 50 degrees Celsius. Now, at 50 degrees Celsius, we have more molecules to the right of the energy barrier with sufficient kinetic energy. And that's why at a higher temperature, we would expect to have a faster reaction rate because there are more molecules with sufficient kinetic energy to the right of the energy barrier. A couple of notes on this graph. As I mentioned before, the total area under the curve of the distribution is the same for both high and low temperatures. That's the key. The area is exactly the same. If we have 100 molecules under the low temperature curve, we have exactly 100 molecules under the high temperature curve. As the temperature is increased, molecules move faster and increase their kinetic energy. This increase in kinetic energy results in a greater number of molecules reaching the energy barrier. Let's now look at what happens to the kinetic energy distribution at two different concentrations. When the concentration of one or more of the reactants is increased, there are more reactant molecules available to form products. Let's draw the kinetic energy distribution at a low concentration. Again, same axes, number of molecules on the y, kinetic energy on the x. And at a low concentration, let's say that this would be 0.1 molar. And we'll draw our energy barrier in here. The molecules to the right of the energy barrier would be available to form products. At a higher concentration, we are actually increasing the number of reactant molecules. So the area underneath the curve does not stay the same. The area underneath the curve will increase when we increase the molarity, and it would look something like this. So let's say this is representative of 1 molar, where the concentration has gone up, and we have more molecules to the right of the energy barrier that have sufficient kinetic energy that can form products. So the curve increases as we are adding more molecules by increasing the concentration. A few notes for this curve here. The total area under the curve or distribution is different for both high and low concentrations. The area under the high concentration curve is greater than the area under the low concentration curve. As the concentration is increased, there are more molecules present, and the KE distribution, the kinetic energy distribution, increases in size. By increasing the number of molecules, a greater number now have sufficient kinetic energy to form products. A general rule is that a 10-degree rise in temperature doubles the reaction rate. The assignment for this lesson is Hebden, pages 19 to 20, numbers 29 to 32.